So, in this video, we're going to write an Arduino library for the Nokia 5110 or 3310 LCD screen. The library is actually going to be for the PCD8544 controller microchip, which controls this LCD screen, and I'll talk a little bit more about that later. Our goal for this at the end of this video is just to write hello world on the LCD. Of course, what else would we write? So you may be wondering, why would you write a library instead of just downloading one? Because it certainly does exist. If you look up Nokia 5110 LCD Arduino, there is a library that exists. Here's one. So here we can just use all of this code and assume that it works, and it should work fine. So some of the reasons for writing a library instead of just using one that already exists is so that you can have a better understanding of the LCD. So if you wanted to modify or update or extend the existing library, if you did want to use it, you would be able to do that. So you can change the functions, change the way it works. Maybe something doesn't work quite the way you want it to, or you want to add some new functionality to it, and then you have the knowledge to be able to do that. Another good reason is just to practice writing Arduino libraries in general. So if you haven't written a library before, or you have, but you want to get some more practice in, it's always good to practice doing that. So in my video, I'm going to be using Emacs as my editor, and the Arduino IDE for uploading the code to the Arduino. So, like I said, the microchip controlling the LCD is called the PCD8544. So that's what our library will be named. And this microchip actually controls the LCDs. So in this case, the Nokia 5110 is what I'm using down here. And so this microchip also controls the Nokia 3310 LCD if you have that one. It may control some other LCDs if you have different LCD modules that use the same controller microchip. So this is more of a general library for controlling all these different kinds of LCDs that use this microchip controller. This controller microchip. And another thing is, I'm going to be using the Arduino Uno, but any Arduino should work with this library because it's more general than that. So let's get started. So we're going to start off just writing the code in an Arduino sketch. So this the sketch I have opened right now, and then we're going to refactor the code into its own library, so into its own .c and .h files. So since we're in an Arduino sketch, of course, we need our void setup and our loop. So this is the bare minimum that you can have for an Arduino sketch. We can upload this, make sure it all compiles. That's good. The other thing is, I've actually already made all the physical connections from the Arduino to the LCD module. As you can see, the wires over here. So those pins are already set, so I need to make some values in my code for those pins. So those are just some digital pins on the Arduino Uno. So I'm going to use some constants for that, and enum. So the LCD pins. So there's the reset pin I have connected to digital pin 6. Actually, I'm going to bring up. I also have the data sheet here, which can make it a bit easier to follow along. So the pins in the controller microchip are described here in this table. And you may notice that there are a lot more pins here that I'm going to have in my code when I write these out. And the reason for that is that these are all the pins on the microchip itself, whereas we are using a module that already has the microchip and the LCD connected on a PCB. And so this module only has the essential pins that we need to control the LCD. So we don't have to have things going to all the pins on the controller microchip, because those are going to the LCD. So I'm just going to finish writing these then. So the SCE pin is Arduino digital pin 7. DC is pin 5. SDN is pin 4. And the S clock is pin 8. So those are in here. So the RES is the reset input. The SCE is the chip enable pin. The DC is the data or command pin. So we'll see all of these in more detail later. The SDN is the serial data input pin. And finally, the S clock is the serial clock input. And there's a short description about these pins right here. And as you can see, the reset pin and the SCE, or the chip enable pin, are both active low. So that's what this bar on top means. So that means they're sort of inverted. So if they're low, as in 0, then that means they're active, whereas if they're high or 1, then they're not active. So we'll just keep that in mind. But even before we get to that, we should realize that all of these pins that we're controlling with the Arduino Uno should be set to outputs, because we are the one giving information to them with the Arduino Uno, not the other way around. So in mode, the reset pin is an output, and we're just going to do the same for the rest. Oops. SDN, and S clock. So all of our pins are now set to outputs, and now, like I said, since the reset and the chip enable pins are active low, and these pins are more important than some of the others, because they actually determine when we're sending data to the LCD. And we're going to look at that in more detail very soon. Since they're active low, we want to start with them being high. So we're just going to say digital write reset pin high, and the same for SCE. So the next thing we want to do, this is a very long data sheet, by the way. It's a very good skill to have, to be able to read a data sheet and go through it and find the useful and relevant information that you're looking for. So I highly recommend using data sheets very often, any chance you have. In this case, we're looking for now how to start writing data to the LCD, because our goal is to write hello world, which is actually characters on the LCD, but we don't know how to do that yet. So we don't know how to actually make characters show up on the LCD. So we need to figure that out. So this is just some information about how the LCD works internally, so that's not relevant to us. This is more of that information about the RAM inside the LCD. The addressing is important to us, but not quite yet. We'll get to that in a bit. What's more important right now is the instructions, because instructions are what we send to the LCD, or rather to that the LCD controller microchip, that it can interpret and make the LCD work as we want it to. So on your own time, you can read more about how instructions are formed here. There's a lot of information about it, so I'm not going to go into all the detail. That can be a whole separate subject matter. But what's important to us, this is how bytes are sent to the LCD. What's important to us is this instruction table right now. Actually, not quite yet. So this instruction table is going to let us know what instructions to send to the LCD and what they mean. So basically how to use the LCD. But even before we do that, we need to initialize the LCD. So this is what's important right now, the initialization. So after we power on the LCD, so after we give power to the LCD, which happens since we've made the connections from the Arduino to the LCD, I've already made those, all the contents of the registers and the RAM are undefined, as it says here. A reset pulse must be applied. And then give some more information. How to do a reset pulse. And after the reset pulse causes the reset function to happen. And when that happens, the LCD driver has the following state. So it has these states, which may not mean anything right now, but what's important is that we want them to have explicit states. If we just power on the LCD and don't give a reset pulse, then since the contents are undefined, we don't know what the states are. So we don't know what sort of mode it's in, what the addressing is, where the address counter is, all these things, the bias system, so basically the contrast of the LCD. So those are all values that we can't assume anything about until we send a reset pulse. So it is important to send a reset pulse. Like it says, a reset pulse must be applied. So after we send that pulse, then all of these internal registers and the RAM get explicitly set to certain values. So to send a reset pulse, so what's a reset pulse? We need to figure that out. So a pulse is generally when a line changes from low to high and back to low, or from high to low and back to high. Because in this case, reset is inverted, so it's active low, and we have it high right now, so pulse is going to be taking it low and then back high. But we need to know how long to take it low for, like how long is the width of a pulse. And that's just down in this next section, actually a few sections. So down here, the reset low pulse width is 100 nanoseconds. And in Arduino, we have the function for delaying microseconds, and 100 nanoseconds is 0.1 microseconds, or 1/10 of a microsecond. And we can't really do any delay shorter than 1 microsecond accurately with the Arduino, but I mean, having a bit larger of a width is fine. And the microsecond is so fast anyway, we're not going to notice that in our code. So then this is just a bit more looking at that a bit closer. And just as a side note, you should be a little careful with some data sheets because they can have errors in them. Unfortunately, this one does. It says this looks like it should be the reset pulse width, TRW. That actually doesn't exist anywhere else. See, this is this is TWL, and even if I do a search in the whole document, there is no TRW. So sometimes there's small errors like that, unfortunately, but we can be pretty confident that this information here is correct. So we're starting our LCD initialization. Initialize the LCD. And we're going to start with the reset pulse for the reset function. So we take it low. And we delay 1 microsecond, and we leave it high again. So that's our reset pulse. And after that, let's go back up. All of these values are now set to what it says here. And these values, you can see what they mean up here, and actually down here as well. So now we can look at the instructions a bit more, because that's really the only thing we need to do before we can just start sending instructions. So when we look at these, the following state, so right now it's in power down mode, since PD equals 1. Horizontal addressing, it's set to the normal instruction set. So all of this is explained in this table and this table. So we can see if PD, if this bit is set to 1, then the chip is in power down mode. But we of course want it in active mode so that the LCD can actually show up or show pixels. We will want to set that to 0. For the addressing, I guess we can look at that now. So the addressing can either be horizontal or vertical. And what that means is up here. So basically how this LCD works is, since it's a graphical LCD as opposed to a character LCD, because that's actually a separate kind of LCD, and those can actually just show characters by having those characters in internal RAM, and then you can just use your own ASCII characters in your code, and those characters will show up on the LCD if it has them in RAM, as opposed to this one where we actually need to set each pixel explicitly. So this is showing the entire LCD. So at the top left here, down to the bottom right, and the addressing for it. And what this is showing is one vertical line of pixels. So this is showing 8 pixels, and this is how we actually send data to the LCD. So we send 8 pixels at a time, and those show up on the LCD in those vertical 8 pixels, and then it moves on to the next part, so the next address, and then we can set another 8 pixels, and we're going to look at that in more detail as well. So for the addressing, it can either be vertical or horizontal. If it's vertical addressing, when we write at the top left, the next address is the one below it, and then the one below that, and the one below that, all the way down to address 5. So from 0 to 5, because this LCD is 84 pixels wide by 48 pixels vertically, but the 48 pixels vertically, we don't actually control the pixels individually by sending a byte for each pixel. We send a byte that controls 8 pixels, because a byte actually has 8 bits in it. So that's why this goes from 0 to 5, which is 6 numbers, as opposed to 48 numbers, because 48 is the number of pixels, but 48 over 8 is 6. So this is the vertical addressing. So if we write the first one, the next address is the one below it, and then below that, and below that, and when it reaches the bottom, it wraps around to the top of the next column. But if we're writing text to the LCD, because we want to write hello world, then this doesn't make a whole lot of sense, because this means the text would go from top to bottom, and then the next column top to bottom, and so on. Whereas horizontal addressing looks like this. So when we write at the top left, the next address is to the right, then the next one's to the right of that, and so on. And that's actually how text looks when we read it in a book or anywhere, obviously. So this is the kind of addressing we want. We want horizontal addressing. So we'll keep that in mind. So let's go back to our instructions. And then these bits just say whether we're using, or sorry, this bit here, the H bit is saying whether we're using the basic instruction set or the extended instruction set. And that's just showing here whether we're using these instructions or these instructions. So we can use any of the instructions in this table, but we need to set whether we're going to use ones in this group or ones in this group by using the function set instruction. And then finally, these can set different modes of the LCD and the temperature coefficient. So those are not as important. We are going to set the mode to normal mode just because that's the mode that we want to use. So the first thing we're going to do is use the function set instruction to set the chip to be active and the addressing to be horizontal, and then we're going to say whether the next instruction we use is in this group or in this group by using this function set, because that's where this H comes in. So up here we see the bits that should be high or low depending on what we want to do. So how these instructions work is the instruction is assigned a certain bit placement where that bit should be the highest bit that is set to 1, so the highest bit that's high essentially, and all the ones below that bit should be set higher or low depending on what we want to do with that instruction. So you can see that in a bit clearer here, even though this has a couple reserved instructions. If you just assume these are all instructions we can use, then you can see the ones here go in a line diagonally like this. So bit 2 is really this instruction, and then bit 3 is this instruction, bit 4 is this instruction, bit 6 is the set Y address of RAM instruction, and so on. So that's basically how these instructions are used and how this table works. And that's going to make more sense once we start writing the code. So if we want to use the function set instruction, that's assigned to bit 5. So we're going to make some constants for these instructions. Function set is bit 5. And in case you're not aware, this is an Arduino function, the bit function. You should read about that in the reference, in the Arduino language reference. It's pretty useful if you're doing stuff like this anyway. So that's our function set instruction. And what we want to do with it, well, we have to think a little bit ahead, because we do have to choose whether H is high or low, so whether the next instruction we use is in the basic instruction set in here or the extended instruction set in here. And if we go back down to here, so after the reset function, we can see what the default values are, and then we should choose what we should set them to be. So we don't want the bias system set to just 0 or the operating voltage set to 0, because that's going to make the contrast just nothing, and we're never going to see any pixels on the LCD. So we do need to set the bias system and the operating voltage. by the way, just before I go on, if we go way down here, there's an example of how you may order your instructions for the LCD if you wanted to start using it. So this example is just showing it uses the function set instruction with these values, sets the operating voltage to this, uses the function set instruction again so we can get back to the normal instruction set, and then sets the display to the normal mode, and then we just start writing data. So we're going to do it similarly to this, but not exactly. So out of all these instructions, what we should do first is set the bias system and the operating voltage, because like I said, this is going to control the contrast of the LCD. So basically the pixels that are supposed to be off versus the pixels that are supposed to be on, and how different they look. So so since we're going to use the instructions in the extended instruction set, we want to set this H to high, to 1, so that we're using the extended instruction set. So I'm going to make a constant for that, and that's function set, and this is the bitwise OR operator. You should read about that too if you're not familiar with it. And then we want the chip to be active, so that is 0. We want horizontal addressing, so that's 0 as well. So we really just want to set this, so set bit 0. Okay, and the way we're going to use these instructions that I'm making is something like this: send command extended instructions. So this is a function we haven't made yet, and we should probably make this now, or we can make this before, or we can keep using it before we make it, just so we can get this out of the way. So the next one we wanted to do is set the bias system. So now we're in the extended instruction set mode, so we can use any instructions here. So we want to set the bias system and the operating voltage. So first let's set the bias system, and that instruction is bit 4. And what we want to set it to is the 1 to 48 multiplexing rate, and I'm not going to go into much detail about that either, because that's a little complicated and that can be a whole nother video. But what is important is to see what these values should be to set that. So BS2 should be 0, and then 1 and 1, and that results in the 4th. So BS2, 1 and 0 should be 0, 1, 1. That corresponds to bits 2, 1, and 0. And that is 48. So that's we're using the bias system instruction, and bits 1 and 0 should be set. Okay, and then this is just set multiplex rate to 148. Okay, and finally we want to set the contrast of the LCD with the operating voltage. And these LCDs are a little bit finicky, so I'm not going to just try to choose the right value, but I'll show you what different contrasts look like when we use it. So set v up, and that was bit 7. Going to start off just with 0. So to set the contrast is basically setting these bits here. So VOP 0 to VOP 6, and so basically it's a 6-bit byte, where the 7th bit it's already set. So I mean, really we could go up to a hexadecimal FF, but it's the same as just doing 7F. But we're going to start with just 0. So all of these are 0 right now. And we're going to see how that looks. And then we can try changing that to adjust the contrast. Okay, so now we actually need our send command to be a function that exists and that works. So let's write that function, send command. The argument for the command, as you may have noticed, this is bit 0 to bit 7, so that's 1 byte. So this is going to be an unsigned 8-bit integer. Call this command. So now how do we actually send a command to the LCD, or an instruction, as you may also call it? Well, that's up here. So this is how we send bytes to the LCD. This is their serial bus protocol. So it's basically SPI, if you have heard of that. If not, this is a timing diagram showing an example of how you would send 1 byte to the LCD. I think it goes into, yeah, it says a bit more detail here. It's instructions, so you can read more about how the instructions work here. So when the chip enable is high, the clock signals are ignored. And then when it goes low, that's when we start sending our data. So you can see when SCE goes low, because it's active low, remember, like this bar indicates, then we can start sending our data. So the S clock goes up and down like a clock, and the data, well, each bit is either high or low when the clock is going up and down. And this is just saying whether we're sending a command or data. So what's important is that SD in is sampled at the positive edge of S clock. So we do need to take note of that. So that means when the S clock rises, so on the rising edge, when S clock is low and then changes to high, that's when this bit needs to be what it should be when it's sent to the LCD. So we know that when SE is high, then we're not sending anything, so we should probably start with that. Just to make sure it's high. It should be anyway, because we set it high here at the beginning, but just in case it's not, we'll set it high explicitly. And then we need to, since like I just said, the data is sampled at the rising edge of S clock, so when S clock goes from low to high, so we want S clock to start off low, so we want to make sure that happens. So we'll set S clock to be low. The next thing that's important is this D/C. So this tells the chip whether we're sending data or a command. So these are all the commands. Well, just basically just not this. So this is the write data instruction, and this is when we're actually writing those pixels, like I said. So those 8 pixels. So when that line is high, then we're sending data to the LCD. Otherwise, when it's low, we're sending any of these other commands. So since this is our send command function, we want that pin to be low. So set that low. And finally, we want to send our data. Now to do this, we're going to use a function in Arduino called shift out, because that basically does exactly what we see here. So just if you just look at these two, the S clock and SD in, so the S clock just goes up and down, and these bits are set to the right values. And Arduino, the shift out function is this. So it shifts out a byte of data 1 bit at a time, and makes the clock go up and down at the right times. And like it says, if you're interfacing with a device that's clocked by rising edges, which we are, you'll need to make sure that the clock pin is low before the call to shift out, which we did. So shift out, the arguments are the data pin, the clock pin, the bit order, and then the value. So the value that we're actually sending. And that value is the whole byte that we're sending. So the data pin should be pretty obvious because we only have one data pin on the LCD. So shift out, data pin is SD in. The clock pin should also be obvious because we only have one clock pin. So LCD pin S clock. And then the bit order, we can look in the data sheet whether it's most significant bit first or least significant bit first. Things are almost always most significant bit first, so we could take a guess and assume that it's that, but we should, should look it up. So we can see the addressing there. So here's instructions. So back to here, if we find the instructions part in the data sheet, we can see that the format starts with the most significant bit and then goes to the least significant bit. So it is most significant bit first, as it almost always is. So MSB first, and that's actually a constant in the Arduino library. And then finally the value that we want to shift out. So our value is command. And if we go back to our timing diagram, where did that go? Here. After we're done sending our command, the chip enable should go back high, so we're not still sending commands. So, and that's it. So that's our send command function. Pretty simple. So we can try this. We can try uploading this, see what we get. So the LCD is not showing anything, and it shouldn't because we haven't actually sent any data to it. We've only sent commands to initialize it. So if we look back in our instruction set, let's just make sure that's all we want to do with our instructions. So we set the bias system, set the operating voltage. The temperature control is not important. We could set the addresses, so set where the data starts showing up when we do start sending data. But if we remember from the reset function, those are actually set to 0 after doing the reset function. So that's at the top left of the LCD. So that's already where we want it to be. What we do want to set is the display control, because we want it to be normal mode, whereas right now, what is it after the reset function? Display blank. So even if we did send some data, we're not going to see it. So we want to set that to normal mode. So D and E should be 1 and 0 respectively. So display control, need to add that to our list of instructions. Put that up here. And that is bit 3. And we want to be able to set it to normal mode very easily. So that's 1 and 0. So 1 and 0. It's basically just bit 2 should be set. There. So set the display mode to normal mode. Actually, that's not going to work, because if we see that instruction is in here, so it's in the basic instruction set, but we're still in the extended instruction set since we made that call here. So we need to get to the basic instruction set. Use basic instruction set. So we need to make that possible. So basic instruction set means this should be low, bit 0. So if bit 0 is low, it's just the same as calling instruction set. Okay, so use basic instruction set and normal mode. So now we can start sending some data to the LCD. So let's say we have a function called send data, and we just want to see something show up. So let's say more pixels is better than less right now. So let's send the byte hexadecimal FF. And if you're unfamiliar with hexadecimal, let's see, 16, so FF, if we look at that in decimal, that's 255, and in binary, it's all ones. So it's 8 ones in a row. So if we look back at pixels on the LCD, if we set all of these to 1, then all the pixels will be on. If they're all 0, they're all off. So a 0 means the pixel is off, a 1 means the pixel is on. So FF just means 8 pixels in a row should be on. So 8 pixels, well, in a column, basically. 8 pixels in the first column should be on. And that may be a little hard to see, so why don't we just set, let's say 20 columns. Okay, so we're setting 20 columns to just be on. And let's upload that and see what we get. I have an error here, probably made a typo somewhere. Oh, of course, we haven't made the send data function yet. So the send data function is going to be very similar to send command, almost identical in fact. Only I'm just going to replace the command parameter with data. The only difference is that this pin here, remember the DC, this is saying whether we're sending data or a command. So in this case, we're sending data, so that pin should be high. All the rest is the same. I just changed the variable name. So now we have the send data function. So we upload that. What do we see? Nothing. It's still blank. And the reason for that is the contrast. So we've still left the contrast at completely 0. If we want the contrast, let's look at the other end of the spectrum. So if we do 7F, so that's just 7 ones in a row in binary. So it's 7 ones. In hexadecimal, that's 7F. So if we set the contrast to that, and the reason it's 7, by the way, is back in our instructions, the VOP is these 7 bits. So bit 0 to bit 6, setting VOP 0 to VOP 6. So if we upload that, what do we see? Doesn't look like, well, it doesn't look like the contrast is showing up. Something else might be wrong. Okay, so there's something I forgot in the send command and send data functions, very important. If we go back to the timing diagram, the chip enable pin should go low when we start actually sending that byte. So I never set that. So here is where it should go low, so right before they shift out. And the same in send data. There we go. And let's try this again. And there. So that's how it looks when the contrast is set fully on. And if we set it fully off, we'll see that that all disappears again. But we want it somewhere in between, because we are setting some pixels here afterwards. So let's try something like 3F. So that's about halfway. It's still all on. Let's try 1F. See how that looks. So that looks good. So let's leave it at that for now. That looks pretty visible to me. Yeah. Could make it a little bit darker. Let's try 28. That looks good. Nice and dark. So that's for setting the contrast. And now we have our contrast set. So this is a pretty good point to start refactoring into its own library. So why don't we do that now? So just going to go to the calculator. And then after that, we'll start making characters, because we can see how to set the pixels, but not how to actually make letters appear on the screen. So we need our header file. Actually, why don't I do it in here? This is our C file in the library. This is where we'll have the pins and the instructions. These functions I'm going to make static because they shouldn't be called outside of this library. Yeah. Whereas we'll have something like initialize the LCD, which will be called outside, and that's going to contain the code that we wrote here. It's already indented. Okay, so now we have our initialization. This should also be in the initialization. Actually, this should be. this is our setting up pins. So we are going to need to share the pins. And this may be changed when I upload it to GitHub, maybe refactored to work a little bit differently. But for now, this is how I'll do it. So there's the pins. And so we want a way to actually have data show up on the LCD. So while we're still just sort of testing things out, I'm going to leave the send data function to be public so we can actually use it in this file. So this needs to be in the header file as well. So that's just the refactoring done. Let's see if it compiles. It does not, because low has not been defined. Oh, I haven't actually included the library in its own file. There we go. And in here as well. So low and high have not been defined in the library. So this is actually going to go in here. We need to include the Arduino library. And this has all those useful constants for us. Now, these errors are actually because of name mangling. So it's trying to use this as a C++ library, but it's actually just C code. So I just need to do a little something to get around that. And there we go. So we're back where we were. Still looks the same. So we can see some lines a little bit in the contrast. So I can actually make the contrast a little bit better so we don't see those lines. So why don't we try a bit of a lower number. Let's just try a nice 20. Okay, so that looks better. So let's so now let's see how we're going to actually write letters, because we know how to write the pixels by pixels, but we want to write letters so we can actually say hello world. So just to sort of show how the pixels work, if we wanted to, let's say we wanted it to show sort of two lines, I guess. We could do something like 5, 5. Actually, 4 lines, I guess that is. Yeah. If we wanted only 2 lines, we could do something like 1, 1, actually. So basically how this is working is we have, well, so one column is like we saw in the data sheet up here. So this is 1 byte. We set the one column of 8 bits to be either high or low, so those pixels. So if they're all low, then it would be something like 0, 0, just 8 times. And then if we have more columns, we can just add more columns. So let's say we want to write a letter. So we want to start with the letter H for hello world. So we need to choose how wide the letters are and how tall they are. A good height to choose would be 8 pixels, since we can control 8 at a time, height-wise. And width-wise, 5 seems to work pretty well for small fonts that are still very readable. So we're going to do 5 pixels wide by 8 pixels high. So 1, 2, 3, 4, 5, and that should be 8 times. Just get rid of these others. So this is our sort of template, all of our pixels. So if they're all zeros, then all the pixels are off. Ones mean that they're on. So if we want to make an H, we'd probably do something like this. So those are all ones. We need the other side. And finally, we need that line in the middle. So that looks like a nice H, a nice capital H. So we need to send the bytes to actually control this. Oops. Here. Let's just make 1H. Comment this all out. So if we just want to write 1H, then we have to send the bytes corresponding to these values. And the most significant bit is at the bottom, the least significant bit is at the top. So when we make it in binary, so in binary, from the bottom up, well, 8 ones is always 8 ones from the bottom up or the top down. So those are 8 ones in hexadecimal. You can see that that's hexadecimal FF. So that's our first column. The next column is this one. So from the bottom up, it's 4 zeros followed by a 1 followed by 3 zeros. So 1, 3, and that's hexadecimal 8. And then that is, that happens 3 times for the middle of the H, and then followed by another whole row of 1s, or another whole column. So there's the 3, and there's our last column. So that's going to write 1H. So let's write that. And there's our H. And as you can see, we still have those lines from before. So those are still stored there because we never actually cleared them out. So let's write a bunch of H's in a row. So let's put this inside here. So let's write, let's say 10 H's in a row. So this is going to be 10 H's. Just to see how that looks. So there's our 10 H's. And as you can see, they actually touch side by side. So when we're writing letters, if they touch side by side, it sort of looks a little weird. So we may want to add a space in between each one. So let's add 1 column of a space, basically. So all the pixels off. And this actually works out well because now instead of each letter being 5 columns, each letter is 6 columns. And horizontally, if we look back in here, horizontally we have we have 84 columns going across, and 84 divides into 6 well. So this back to decimal, 84 divided by 6 is 14. So it actually divides evenly. So that works out well, because then if a letter is at the very edge, it won't be wrapped around in the middle of the letter onto the next line. It'll actually wrap around nicely. And we can see that if we write a lot of these. So let's write 30 of them. So that's going to go past the edge, because the edge stops at 14. So if we write 30 of them, it looks like this. Yeah. So it does wrap around automatically, like it shows here in the horizontal addressing, which is what we're using. So it goes from the top left all the way to the right, and then on the next row, starting at the left and going to the right, and so on. So now we want to write the rest of the alphabet, and we don't want to have to write each one manually like this. So what we're going to do is use an ASCII character array that's already made. So we are going to use some code that's already made, and this is look up Nokia 1510, Arduino. Let's go back here. So this array here is what we're going to use. So this here, because this has all the letters already made for us. And if we were going to make them ourselves, we'd probably make them the same way. There's not very many different ways you can make the same small characters. And I actually have that here. I was using it for something else. So I'm just going to put that in our in here. So this is our array of all of the ASCII characters that we can write on this LCD. Now, notice that this starts at hexadecimal 20 for a space. This is the space character, and actual ASCII starts at 0, like this. So it starts at 0, and hexadecimal 20 is still space. So this does correspond to actual ASCII, but it's 20. It's hexadecimal 20 ahead of what is usually ASCII. So that will be important in our code. So let's change this back to static now, so that this is private to this library, and get rid of it here. And instead, we want a way to easily just write a string. So we can just write hello world instead of saying send an H, send an E, send an L, send an L, and so on. So we want to be able to say, we want to be able to say write hello world. So we need an LCD write function. And this function's argument will be a string of characters. And this is going to write each character one by one until it reaches the end. But we need a function to write each character, because we don't quite have that yet. So we need, and this will be a private function. So this can just be send character, send char, and its argument is one character. Let's call it C. And now we know the width of the characters is 5, and I'm just going to hard code this in for now, but it's not good to have magic numbers generally. So I is less than 5. and you want to send data. This is our so this is our array of all the characters we can use. Each one is 5 bytes in width, so its location is going to be C minus hexadecimal 20 at the place of I for each part of that character, and then, like we saw, we want to send a little break in between each character, so each one is actually 6 in width, 6 pixels wide. So if I were to put an H here, this ASCII value of the H would correspond to the same location in this array minus hexadecimal 20, because like I showed, actual ASCII is ahead by 20 because of those 20 extra values at the start. So that's it for that. So that's how we send a character, and if we want to send a string of characters, we can just say while the current value in the string is not null, send the character at that place, and afterwards increment it to the next and the next character. That's just a really compact way of writing it. And now we have our hello world. Let's see how that looks. We have an error because I haven't actually declared this function. Actually, this should be after init. A string to the LCD. And there we go. So now we have hello world. And I'm going to go a little bit further just because we still have the H's there, and it would be nice if we didn't. So let's say we wanted this the LCD write function to do a little bit more. Or actually not the function to do more, but we want to be able to do more. So we'd like to be able to clear the LCD. This is even easier than the LCD write function. This takes no arguments. So this is just going to get rid of all the characters or all the pixels on the LCD. It should set them all to be off, so the LCD is clear. So we start at 0, and then we want to go through all the different placements on the LCD. So it's 84 by 48 over 6. So 48 over 6 is 8 times 84. Sorry, that's not right. It's so we have in here. Well, basically it's 84 times 6. No, sorry, that should have been 48 over 8. So 48 over 8, yeah, 6 times 84, so 504. So that's all the different. That's how many bytes we can write to it. Send data, we want to send zeros. And for this, we want to make sure we're starting at the very top left. So we're just going to quickly write the instruction. So a couple instructions we haven't used yet. Set Y address and set X address of round. So this sets where we're going to start from for writing to the LCD. So set Y and set X. So set Y is the bit 6. Should come after display. And set X is bit 7. Okay. So we'll set Y first. And then set X. So we're setting them both to be 0. So if we set all these values to 0, then we're setting the address to be 0. And let's do the same for LCD write, just so we're always writing from the top left as well. So in case the address is somewhere else, because after we run this command, the LCD clear, it's going to be at the last address. And it may loop back to the start, but we want to explicitly make this start writing from the start. So we'll clear the LCD and then write hello world. And let's see how that looks. And we need to actually have this function available to us. And there we go. Hello world. So if you have any questions, please leave a comment and I'll try to answer it as best I can. The code will be available on GitHub. I'll put the link in the video description, and thanks for watching.